Okay, so we'll just talk about another algebraic structure is called ring. So before that, we just recap the what we said about group and some more properties on the group. So we have seen for a group we need to have a operator. We have a set G and we have a operator, binary operator dot, and if it is group if it satisfy few properties we have seen, closure, associativity, identity element, existence of identity element, and inverse. So if these four properties satisfy, then it is a group, and along with this, if a extra property, commutative property or abelian property, if it is commutative, abelian, then this is called the abelian group. It is called abelian group or the commutative group. Okay. And then we talk about a cyclic group. Basically, it is having a generator A. So, it is having a generator A which generates the group. Okay. Now, if we take, so now we talk about subgroup. Subgroup is basically, so if you take a subset of G, which is basically say H. So, H is a subset of G. Now, if H along with this form a group is a group, then we called this is a, then it is called a subgroup, because it is basically subset. Okay. Now, if we take an element from A, any element, let A be a any element from G. Okay. Now, if we take this set A square, A cube, like this, A to the power I, like this. So, this is a subset, because the closure property of G, all the elements must belongs to G. So, basically it is a subset. So, we have a set G and we are taking a subset H from here, which is basically the elements are basically generating by this element A. Okay. And then after some times it will give us the identity element. Say suppose that is A to the power n is equal to E. So, n is the least integer, minimum natural number for which A to the power n is equal to E. Then n is called order of this element A, or basically it is order of this. So, this will form a subgroup. Then this H along with this is a subgroup. And this order of this subgroup is basically this n. This is basically cardinality of H, and this is also called order of that element. So, if you take any element and if you take the subset or subgroup generating by this element, by keep on applying this element, then it will form a subgroup, and this subgroup is basically order is the order of that element. And there is a theorem which is telling, Lagrange's theorem, that order of a subgroups divides order of the group. So, I will come back to ring. So, before that let us just talk about some properties of a group. So, this theorem are telling order of a subgroup divides order of a group. So, that means order of that cardinality of H divides cardinality of G, provided they are finite. If they are infinite, then this has no meaning, because both are infinite, I mean both could be infinity. Okay. So, provided they are finite, then order of this group, order of subgroup divides, so this is divide, we will formally define. Okay. So, this is a subgroup. Now, we have seen a group is cyclic if it has a generator A such that all the elements is of this form. C is another element, C will be of this form. So, basically A generates the group, then it is called a cyclic group if such A exists, and then A is called a generator. And this is a abelian group, because in that case everything in this form, every two element B C of this form A to the power I, C will be A to the power j. So, B into C is basically A to the power I plus j, which is basically A to the power j plus I, which is basically A to the power j into A to the power I. So, this is basically C into B. So, it is always abelian. So, every cyclic group is always abelian. Okay. So, now we will talk about the ring. Okay. So, for ring we need to have a set G, or this set is denoted by say R G. We will just this is a ring, that is why it is R, and G is the set. So, R G, but here we have two operations, one is plus, another one is additive sense, another one is multiplicative sense. Here we have two binary operation. So, one is plus, one is multiplicative sense, and this is our set, and this is satisfy, if this is satisfy following four properties, then it is called a, this algebraic structure is called a ring. So, first property is telling it must be a abelian group under the plus operation, okay. And then second property is telling with dot operation or with the multiplicative sense, it must be a closure property must satisfy that. So, that means it is a semi ring under dot, and some extra property like distributed property, this is dealing with both the operation. So, if this satisfy, then it is called ring. So, what it is telling? So, first of all, this R, this set along with this must be a is an abelian group. Okay. So, abelian group means it must satisfy these four properties, 5 properties like closure. So, if we have two element A B, so A plus B must belongs to R G for all A B belongs to R G. This is the closure property. And second one is associativity. A plus B plus C must be equal to A plus B plus C, and this must true for all A B C. Okay, this is the associativity property. And third one is existence of identity. So, there must exist a identity element E, which is for additive sense it is referred as 0. So, A plus E, that 0 is equal to 0 plus A is equal to A for all A belongs to this set, and this is basically identity element under the plus operation. And then the existence of inverse. So, every element should have inverse under this operation. So, for a given A, there must exist a inverse, which is denoted by minus A, such that A plus of minus A is equal to identity element. So, this is basically B. So, A operate B should give us the identity element. So, this is the existence of inverse. So, if these 4 properties satisfy, then it is a group. Now, we need to have a abelian group. So, that means we should have the commutative property. So, that means A plus B must be equal to B plus A for all A B belongs to R G. So, if these 5 properties satisfy, then it is a group under this binary operator plus. This is not a real number plus, this is a operator, we are just referring as a plus for simplicity, but don't think that it is a real number plus always. We will check whether real number plus will form a ring or not. Yes, it will form a ring, but this plus is, you can think general operator. Instead of plus this, we can use some star, some another operator like this. We have a group R, we could use that, but anyway to simplicity we will refer plus and this as if additive sense one operation and another operation is in multiplicative sense. This is for the simplicity purpose, but we could, one can always derive all these things using the general symbol, but anyway what is there in the symbol. So, this is a abelian group. So, it must satisfy these 5 properties. Okay. Now, next is this is on with the plus operation, and then the next is with the dot operation, it must be a semi group with the multiplicative sense. Semi group. So, semi group means it must satisfy 2 property basically, one is closure property. So, that means for any 2 element A cross B or dot, this is multiplicative sense, it is basically this cross is belongs to R G for all A B belongs to this set. Okay. So, this is the closure property, and then the associativity also must satisfy. So, this is basically telling us A dot or this okay. So, this is the associativity. If this satisfied, then we call this is a semi group, and then along with some property which is related to. So far there is no combination of these 2 operators. So far we are dealing with independently these 2 operators. Now, this property is telling the distributive property which is involved there together both. This is the distributive law or distributive property. It is telling us, so A dot, I mean A cross B plus C equal to A cross B plus A cross C, and this is true for all A B C belongs to R G. Okay. We have to understand this. So, B is an element in R, C is an element in R. So, if you operate B plus C and plus is a closure under R is closure under plus. So, this will be an element in R. So, since it is an element in R and we know this operator is closure. So, we operate A with that another element in R. So, this will be also an element in R. So, this element must be same as, if we element so this is A in R, B in R, B in R. So, if we operate this will be in R, because closure property is satisfied under this multiplicative sense. Okay. And then this is A in R, C in R. So, this A cross A multiplies C is also R. This is not real number multiplication, this is a some operator. Okay. But for simplicity we are taking the real number sense like plus, dot. Then these 2 are, this is belongs to R, this is belongs to R. Then we know plus is an closure. So, we can add these 2, we can take under this operation, this will give us the element in R, but that element must same as this element, and this must true for all ABC, all ABC. Then if this all this I satisfy, then R is called a ring. R along with plus R G is called a this algebraic structure called a ring. Okay, so we can take some example of ring. We can take some example of ring. Okay, so if we take this set I, or if we take this set I, set of integer and plus real number dot, is this a ring? So, we have to check I plus, this is an abelian group, this we can easily verify, this is an abelian group. So, and second one, we have to check this along with this dot is a semi group or not. So, for semi group we need to have the closure property and associative property. So, this is a semi group, because if we take any two integer, if we multiply these two, it will give us an integer, closure property is satisfied, and associativity is also satisfied by the associativity law of the dot, the real number multiplication is a semi group. So, now we have to check the distributed property. Distributed property is telling if you take any three integer a, b, c, then a dot b plus c is equal to a dot b plus a dot c. This is also true. This is true from the law of these two operator plus and dot of real number. So, this is an example of a ring. Okay. So, now come to the slide. So, this is the distributed property. So, now we call a ring is a commutative ring if on top of this all these properties, if we satisfy the commutative property under the dot, under the multiplicative sense, because we know already it is abelian group under plus. So, if it is commutative ring means it must be commutative under this dot. So, commutative ring or the abelian ring we can say. So, first of all this R G we can use this or this. Okay, this will be commutative ring. First of all, this has to be a ring. It has to be a ring, and then this we know ring means it is already commutative with this plus operation. So, now the commutative means it must be again commutative under this multiplicative sense. So, that means for all a b belongs to that group a cross b, a dot b is equal to b dot a. So, that means this is an abelian, this is commutative. Commutative operation. Okay. So, if this is satisfied, so this is also a commutative ring. I didn't this set of all integer plus dot. This is a commutative ring, because this operation is the real number multiplication is commutative. Okay. So, now after commutative ring we will define what is called integral domain. This is also another algebraic structure which is basically having two property, two operator, integral domain. Integral domain. So, we say a ring, I mean we say a group along with these two operation is an integral domain. First of all, it has to be a commutative ring, and the multiplicative identity should exist. So, multiplicative identity. Multiplicative identity means this we already know this is a group. So, it has a inverse, it has a identity element under this operation, but whether it has a inverse, it has a identity element under this dot. So, multiplicative identity. So, that means there exists a E. E is referred as 1 basically, because this is in multiplicative sense. There exists a E such that A dot E must be E dot A must be A, and this must be true for all A. And this E usually referred as 1. So, 1, I mean just the symbol, E is an element, E is an element in R G. So, E is unique. So, E is, since it is multiplicative sense, it is 1. It is symbolically, it is just symbolically, because it is a general definition. It is not that it is a definition, it is not that it is we are dealing with only real number. So, 1 into E, sorry, 1 into A is equal to A into 1 is equal to A. So, then it is called multiplicative identity. So, this is this property M5. So, for every element, if we operate this with the identity element, and it should give us A, it should be equal to A. Okay. And it should not have no zero divisor. This is another property. So, that means, if you take any two element A B from this set, and if A B is equal to 0, then either A is equal to 0 or B is equal to 0. So, this is the no zero divisor. So, if A dot B, this is the multiplicative sense, is 0, then either A is equal to 0, then B is equal to 0. Then it is called no zero divisor property. Then this, if all these properties satisfy, then it is called a integral domain. So, another is no zero divisor. Okay. That means, if we have A dot B is 0, then either A is 0 or B is 0. Okay. So, then if this 4 properties satisfy, then it is called an integral domain. Now, we will talk about field. Okay, we talk about field. So, for field also, field is also an algebraic structure. Here also we have a set, and we have two operator plus and dot, and so it also must satisfy some properties. So, first of all, it has to be an integral domain. It has to be a integral domain. Okay. And this it should every element should has inverse under the multiplication. We know every element has inverse under plus, because it is an integral domain. So, that means, under plus it is an abelian group. So, since it is an abelian group, every element has a inverse. So, we want the inverse also under this dot. So, that means so inverse, multiplicative inverse, existence of multiplicative inverse. So, every element should have multiplicative inverse, that means every element should have inverse under this dot operation. So, that means for a given element, for a given A belongs to F, there exists a B which is in F such that A operate with B is equal to identity element of multiplicative sense is equal to B operate with A. Okay. So, this is basically this is usually B is usually symbolically referred as A inverse. So, this is the multiplicative inverse, inverse others with the other. So, if this exists, if for every element, for a given element A, it has a inverse. Okay. So, basically this is our F. So, given A, if we have a element A which is B, basically A inverse we refer, and if we multiply this, it should give us identity element of 1, and this is not for all element, this is other than the identity element of plus. So, other than 0. So, other than this identity. So, A is basically A is coming from F minus 0. So, because this 0 is the identity element under plus, additive identity element of plus, it has no inverse basically. So, other than this 0, it should have a inverse. So, this should be there. So, now if this satisfy, then it is called a field, then this F along with this operation is called a field. So, basically what we have this. So, this integral domain is a field. So, basically for field, this must be an abelian group, is an abelian group, and also F minus 0 is also an abelian group. I mean, we can use this anyway, this is in multiplicative sense, is also an abelian group. Okay. Then we called this is a field. So, if this and also the distributed property like A dot A cross B plus C is equal to A cross B plus A cross C, because this is the property in the integral domain, it was there. So, it is, if this satisfy, then it is called a field. Now, let us take some example of field. So, field has good application in cryptography, especially finite field. Finite field means if the number of element in G is finite, the cardinality of this set F. So, example of field. So, set of real number plus and dot multiplicative sense is a field. Why? Because we have seen this is an abelian group, And also if we just remove this 0, 0 is the identity element for plus, because 0 has no inverse under multiplication, because 1 by 0 is not defined in real number system. We can have extended real number system, there we can define 1 by 0 as a symbol infinity, but anyway real number is not consisting 1 by 0 as a element. So this is basically, anyway we do not need to bother about this, because for field the 0 this identity element of this plus is not having the inverse, I mean we do not care about that. So this is also an abelian group. Okay. Now, yeah, so this is also abelian group, and also we have this distributed property. If you take any 3 element A, B, C from this real number set, we know A dot B plus C is equal to A dot B, sorry, A dot B plus B dot C, A dot C. This is the property of the plus and dot in this. So this is an example of a field, but this field is an infinite field, because cardinality of this is infinity. There are infinite number of points in the real numbers, they are infinite, but if the cardinality of R is finite, then it is called finite field. We will talk about finite field after talking the number theory. This is the hierarchy of the algebraic structure. So if we have this closure property, so we have basically two operator, addition and the multiplication. So this is the closure property under addition, and this is the associativity property under multiplication. This is the associativity property under addition, and this is the identity element of addition, and this is the additive inverse. So if this we have this 4, then it is a group, and along with that, if this plus is commutative, then it is called abelian group up to this. And then for ring, we have another operator which is multiplicative sense, which is dot. Now if for ring, it must be a closure and the associativity and the distributed law, then up to this, then it is called a ring. And then if it is commutative ring, means we have this dot is also commutative operator, A dot B is equal to B dot A, and then for integral domain, we have the inverse, multiplicative inverse. So A dot 1 is multiplicative identity. So A dot 1 is 1 dot A is equal to A, 1 is the multiplicative identity, and no 0 divisor. If A B is 0, 0 is the identity element of plus, then either A is 0 or B is 0. And then if we along with this, if we have the multiplicative inverse for each element in A other than 0, then it is called a field. So this is the hierarchy of the field. Thank you.